Hello, welcome again. We are solving GATE 2016 Aerospace Engineering paper. Question number 36 is consider the following system of linear equation 2x minus y plus z is equal to 1, 3x minus 3y plus 4z is equal to 6, x minus 2y plus 3z is equal to 4. This system of linear equation has option A no solution, option B one solution, option C two solution, option D three solution. So taking this in form of in the matrix form and taking the augmented matrix, so it will be 2 minus 1 1 and 1, 3 minus 3 4 and 6, 1 minus 2 3 and 4. Okay, so this is the augmented matrix. So operating R2 and then performing operation and operating R2 as R2 minus R1. So this will remain same, this will remain same, and just we are changing this. So it will be 3 minus 2 1 and minus 3 plus 1 minus 2 and 4 minus 1, that is 3, and this is your 6 minus 1 1. So now performing second operation to R3, so taking R3 minus R2, so 1 minus 1 0, minus 2 plus 2 will be 0, 3 minus 3 will be 0, 4 minus 5 is your minus 1. So now we can see that this is your 0 0 0 and this is your minus 1. So coefficient rank of this is your coefficient matrix, and the rank of coefficient matrix is 2, and rank of augmented matrix is 3. So these ranks are not equal, and so it is having no solution. So answer is option A. Next, question number 37. A bar made of linear isotropic material is fixed at one end and subjected to axial force of 1 kilonewton at other end. The cross sectional area of bar is 100 mm square. The length is 100 mm. The Young's modulus is 10 to the power 1 into 10 to the power 5 Newton per mm square. The strain energy stored in the bar is dash Newton mm. So axial force is given as 1 kilonewton. Okay, and cross section area is given as 100 mm square, and stress is your 1000 by 100, that is 1000 by 100 Newton per mm square. So E is your Young's modulus elasticity 1 10 to the power 5 Newton per mm square, and strain is stress by E, so that is 10 by 10 by 5 or 1 by 1 10 by 4, and length is your 100 mm. Length is your 100 mm. So change in length is change in length is original length by strain, or that is 1 by 100 mm. The strain energy is nothing but force into change in length by 2. So now force is your 1 kilonewton or 1000 Newton, and the change in length is 1 by 1000, sorry 1 by 100, and if you multiply it by 1 by 2, so that is the strain energy will be 5 Newton mm. Okay, so answer is 5 Newton mm. Next, a cantilever beam spring system is shown in the figure. The beam is made up with a material of Young's modulus 1 into 10 to the power 5 Newton per mm square, and geometry such that its moment of inertia is 100 mm force, and length is equal to 100 mm. It is supported by a spring of stiffness K is equal to 30 Newton per mm, and subjected to load of P is equal to 100 Newton at point B. The deflection at point B due to load P is dash mm. So this is your P, and this is AB, this is length L, this is K, stiffness of P. Okay, so now let W be the compressive force which is compressing the spring, and as W is not acting, so we will take W in opposite direction also. Now the net load on the beam, such that the net load on the beam on the cantilever will be P minus W, and net load on the spring is W. So compression in the spring will be equal to deflection of the cantilever, and compression of the spring is caused by W, and that deflection in the cantilever is caused by P minus W. Okay, so that is so that deflection is W by K, and sorry, that compression is W by K, spring compression, and that deflection is P minus W L cubed by 3 EL. Okay, so putting that value, sorry, solving this, we have W by K plus WL cubed by 3I plus is equal to PL cubed by 3I. Okay, so now L is given as 100 mm. Okay, so L is given as 100 mm, and EI is spring stiffness is 30 Newton per mm, and moment of inertia is 100, and E is at 1 10 Newton per mm. So putting these values, we can get W. Okay, so W is your 50 Newton. So after getting W, we can find out the reflection of spring, that is W by K. So that is 50 by 30 or 1.6667 mm. Next, determine the correctness or otherwise of the following statement A and R. Option A, small a, ribs used in airplane wings increase column buckling strength of the longitudinal stiffness. R, ribs distribute concentrated load into the structure and redistribute stresses around the discontinuity. Option A, both A and R are Q and R is correct reason for A. Option B, both A and R are true but R is not the correct reason for A. Option C, both A and R are false. Option B, A is true but R is false. So answer is option B, because these are individually correct, and this use the statement A. These are used for increasing the strength against column buckling, and they also distribute the redistributed stresses around the disc. Okay, so answer is option B.